Okay, hi guys. So we'll be continuing on seeing more on second order kinetics. So far we have seen that Kr was equals to 1 upon a minus bt ln a minus x divided by b minus x multiplied with b upon a. So now if b is taken in axis, then we can write that a minus b would be minus b and b minus x would still remain b. Okay, so substituting these values in the above equation, we can write Kr would be equals to 1 upon t minus b and ln a minus x divided by b upon a. So b and b gets cancelled out. So this minus sign, if we incorporate in the ln term, we will getting 1 upon t or 1 upon bt rather ln a upon a minus x. So this is the rate constant. From here we can calculate t as 1 upon k ln a upon a minus x. So where k is the rate constant of pseudo first order reaction. Okay, and why we are calling it pseudo first order reaction? Because this term looks similar to what we have already seen in first order reaction. So rate constant, k is rate constant for pseudo first order reaction. Okay, now let us see an example. We have CH3 C2H5 or other CH3 C double bond O C2H5 CH3 C double bond O C2H5 aqueous plus H2O aqueous. This gives us CH3COOH aqueous plus C2H5OH aqueous. So this is in axis. So we can write that suppose the rate of reaction is rate constant times CH3CO C2H5 to the power x and H2O to the power y. So we can write that what is a pseudo first order reaction. So pseudo first order reaction in this case can be wherein we can write R is equals to K times CH3 C double bond O C2H5 to the power 1. X becomes 1 and K can be written as Kr times H2O L to the power y. So this is a pseudo first order reaction in which we can write R as K times CH3COO C2H5 to the power 1. This is an example of pseudo first order reaction. Okay, so let's now see any nth order reaction. So suppose we have Ag getting converted into Bg plus Cg. So here we can write that initial concentration again was, let's say, A, when these two are not present. Concentration at time t, let's say it was X was dissociated to form concentration of B and C both as X. So we can write that dx by dt was equals to K into 1 minus x to the power n, because it's a nth order reaction. So from this we can write that dx divided by a minus x to the power n, just rearranging the terms for the integration, k dt on the right hand side, Now just applying the integration, so we'll be getting 1 upon n minus 1, 1 upon a minus x to the power n minus 1 would be equals to kt plus c. So now t is equals to 0. When t equals to 0 and x would also be equals to 0, from this we can calculate the value of c. Okay, so we can write that c would be nothing but 1 upon n minus 1 times a to the power n minus 1. Or we can write that when we substitute the value of c here in the original equation, we would be getting that k would be equals to, let's go step by step. So we would be getting 1 upon n minus 1 a minus x to the power n minus 1 should be equal to kt plus c would be 1 upon n minus 1 a to the power n minus 1. Just rearranging it, so on the left hand side, taking this term on the left hand side, we would be getting something like 1 upon n minus 1 is the common denominator in both the sides, so taking this part out on the LHS, so we would be getting 1 upon a minus x to the power n minus 1 minus 1 upon a to the power n minus 1. This would be equals to kt. So finally we can write rate constant for the nth order reaction as 1 upon t into n minus 1 multiplied with 1 upon a minus x to the power n minus 1 minus 1 upon a to the power n minus 1, where n cannot be equals to 1. Okay, so this is a very important formula to remember. Directly put the value for calculating the rate constant in examinations, so you don't have to go through the pain of deriving each time a similar question is asked. Just put in this formula and you will be happy. Okay, so let's actually also calculate the half-life. So we know half-life would be time at which concentration of the reactant drops to half of its value. So x would be equals to 1 by 2. So t half would be nothing but 1 upon k n minus 1. Just put x as equals to a by 2. So it would be 2 to the power n minus 1 divided by a to the power n minus 1 minus 1 upon a to the power n minus 1. So we would be getting t half as 1 upon, rather we can directly write t half is inversely proportional to 1 upon n minus 1. So you can very well simplify it, so that's not a big issue, so I'm leaving it here only. So t, the main point I'm trying to make here is t half would be proportional to, or rather inversely proportional to a to the power n minus 1. So for a third order reaction, we can write, for example, for third order reaction, we can write as n equals to 3, we can write t half would be proportional to inversely proportional to a square. And if we draw the graph of the same of t half of third order reaction, third order with let's say 1 upon a square, then this would be a straight line. Okay, so with this we come to the end of this lecture. In the next lecture we'll be seeing experimental determination of order of reaction. So till then, good luck and goodbye.